Everyone, welcome to this lecture of mixed signal IC design. So we were discussing about comparators, and in the previous class we discussed one comparator based on the idea what we have developed from here. So in continuation with that, so we were discussing clocked comparator. So in continuation we'll discuss one more type of comparator in today's class. If you look at the previous comparator circuit, you have one thing or one disadvantage what we have mentioned is it's having a lot of clocks like 515253, and maybe one more clock is required for the proper operation of the comparator. So that is the only drawback what we can mention about this specific type. So why it is a drawback is because generating those many clocks and distributing the clock, and when you will have the circuit with a lot many other digital blocks, right? So that is a challenging task. That is the way how these number of clocks will, yeah, that is how that is why we call this as a disadvantage in this particular type of comparator. So in continuation with this, in today's class we'll continue with this clocked comparators, one more type, and then we'll come back. After this, we'll come back to the regular comparator. Right. So in between, if you have any questions, you can put it in the chat box. I hope the screen is visible, right, and my audio is clear. All right. Fine. So in the previous comparator, when we were discussing, what we saw is the basic structure what we have is kind of you'll have you'll have back-to-back inverters which forms a regenerative pair, right? This is how we have seen the basic structure, and then a few modifications on the same structure in order to work it as a like in order to resolve the analog value to a proper logic 0 or a logic 1, and this is a basic structure, right? So and one more from the previous discussion, one more thing what we noticed is it basically it works in like there will be two phases of one will be a reset phase where we will be resetting the latch or the latch based comparators. We will be resetting to in order to erase all the past memories of the comparator, and the second phase is basically the regeneration phase, or we can call it as the amplification phase, like amplification or the regeneration phase, where the difference or based on the input what we have, we'll make a decision by regenerating the output to either a plus 1 or a 0, or a plus 1 or minus 1, depending on the voltage levels what we have, right? So if you look this as a regenerative pair, so this is a regenerative pair. So in general, how we can reset is basically, say for example, if this node I have Vm plus Vd, and if this node is Vm minus Vd, one way of resetting, or not regenerating, one way of resetting is shorting these two and give a clock here and short these two nodes, so that these nodes, both the nodes will be shorted and will come to a common voltage Vm, which will disable the regenerative latch. Thereby the output can be set to a common value in the sense from there only we'll start the comparators will start working, right? So this is how we generally short or will make the voltage or to disable the latch, this is what we do, and this time there is no positive feedback present. As a result, the latch will be disabled basically, right? So this is a basic regenerative pair what we have seen before. Now in today's class we'll look at another type. So as we are discussing about clock comparators, in the previous comparator we had multiple clocks. Today we'll discuss about one specific type of comparator which is based on a latch we call it as strong arm latch. Strong arm latch based comparator. Now this specific architecture what we are going to discuss, by the name strong arm latch, is basically because this is used in strong arm microprocessor. Because of its usage in the strong arm microprocessor, which was developed by a Digital Equipment Corporation in I think 90s. In 90s, this architecture was widely used in strong arm microprocessor, and that is why this latch is named as strong arm latch. But the original circuit, or the classic strong arm latch circuit, is proposed by Toshiba, the company, the people in Toshiba. All right. So compared to the previous comparators, or compared to any comparators, generally strong arm latch comparators will have a lot of advantages, and one main advantage is it's almost zero static power. There is no static power consumption in a strong arm latch. Reason is one thing. As you can see that here I have a back to regenerative latch, right? And as I said that during a reset phase, the output will be reset to a specific value. And when I'm doing the reset, I'm disabling the latch. So if you look at this state, say if I'm resetting, what happens is, if I have a reset in this form, in the strong arm latch comparator, it also made sure that the inverters are not operating. Inverters not operating in the sense, the inverters will not draw any current even in the reset phase. It is not like we'll have a short and the inverters will be working, but still the output will be reset. It is not in that way. Rather, inverters will not consume any static power. So zero static power is one advantage, or one of the most notable advantage of this strong arm latch. All right. So the basic architecture. So let us discuss about the basic architecture of this strong arm latch. How this works is, it is based on this back-to-back inverters, which helps in regenerating, and it also will have a reset signal coming in, so that reset will happen and the previous memory will be erased. Now see, whenever you have an input signal, and we are assuming that the input signal is available in differential form, so that a small input differential signal will be applied. So the basic idea here is, here we will after resetting the circuit, or after clearing the previous state, so we know that if you have a signal, say if I have a common mode voltage VCM plus VD and VCM minus VD, what I should get is, based on the input signal, if the latch is a regeneration type latch, the output should regenerate and finally come decide, or finally the output should tell the value, either it should regenerate to 1 or 0 based on the input value. This is what we need, right? So here we'll apply VCM plus VD, here we'll apply VCM minus VD. And the initial condition for regeneration is generally established with the help of current sources in this form. So when I say current sources in this form, in the actual circuit we get this through with the help of a differential pair, right? So for example, this arm is carrying IP and this is carrying IN, where both IP and IN are in proportion with the input signal VD. So how are these related? If you have input signal VD and minus VD, your IP and IN will be GM times, right? So that is a small signal relation what we have. So this is the basic structure of a strong arm based latch. There are various there are various modifications are proposed, but what we will be discussing will be the classic strong arm latch. Are you guys with me? Can I get some response in the chat? All right, yeah, fine. Yeah, so we have the regenerative latch, then we have this reset signal or the reset switch is there, and then the initial condition for regeneration is basically established with the help of, I'll just write it here. This is the initial condition for regeneration is established in this form. Right. Now what we'll do is we'll convert this model into the circuit, or we'll draw in terms of circuit here. So back-to-back inverters we can replace with the circuit of inverters. And now for the initial condition for regeneration is established with the help of current sources. One way, or in basically in the strong arm latch based comparator, how yeah, so this is yeah, this is the image of the strong arm that strong arm processor what I got from internet. So all right, so what we do here is we'll draw the circuit of the strong arm latch based comparator. Mm, so what we know is we have back to back inverters, so let me draw that first. These are the back to back inverters. uh, Now this should be connected, so from here the connection is towards this side, and from here output the connection is back to this side, and this is the VDD line. Now both the output nodes should be reset. So reset is generally done as a reset to VDD. There are other forms as well. This is the classic form. Right. Maybe what I'll do is I'll just use a different color just to recognize that this is your reset signal. All right, and now the initial condition to establish regeneration is given, or what we need is some the model or the previous when we discussed it is in the form of a current, in the form of two currents, small signal current, and that is generally done with the help of differential pair. So from here we'll have the differential pair, which is also a clogged differential pair. All right, so this is the structure what we have. Now let me name this. So this is the input differential pair. Now let me mark it as this as VIP and this as VI plus and minus. So together it makes the differential voltage VID. Now this is the clock, right? So I'll just mark it as CLK. There is one clock. As I mentioned, we'll use only one clock here. Now these four transistors forms the back-to-back inverters. So let me just name this as MP1. This is MP2, MN1, and this is MN2. That forms the PMOS and NMOS of the inverter. Now this is the input transistor pair. So MI1, I'll just mark it as MI1 and MI2. All right. Apart from this, I'll also mark the nodes. So these two are the output nodes. So let's mark this as VOM and this as VOP. All right. So this, just mark another node here. So that's Vx. So this is M and this is P. All right. Now, so I hope this circuit is clear. What we have done here is, so this is a circuit diagram, and what we have done here is we have taken the basic back-to-back inverters for regeneration. We have this back-to-back inverters for regeneration, and then we have this the clock. We have the switch which will keep your output to output reset, and then we have this the circuit to establish the initial condition for regeneration. All right, so this I mark it as IP and this is IN. So similarly, what I can see is this will carry current IP and this will carry current IN. Right. Now what should happen is, whenever there is a differential or whenever there is a small whenever there is a signal available at VIP and VIM, the circuit should make a decision whether that can regenerate to 1 or regenerate to 0. Right, that is a operation what we are expecting out of this. All right. So this is a clock comparator as we mentioned. So if you look at the circuit, we can see that there is a differential pair which is clocked because it works on this the tail current source. It is basically a clock. There is a switch connected with the clock, so we call this as clocked differential pair. This is a clock differential pair. Then what we have here is back-to-back inverters which forms the cross-coupled pair for regeneration. And finally what we have is switch. So in this classic strong arm latch type, we have only we'll be resetting only this node, the node here what it's marked as VOM and VOP only we'll be resetting, but there are other versions. I'll after discussing this, I'll tell you one paper what we can go through so that you will understand more about this type of comparator. We have switch for pre-charging or resetting. Right, so these are the basic components in the circuit. Now let's look at the working of this strong arm latch. What happens is since this is based on a clock, we will look at the working in under two phases. One when the clock is low and the other one the clock is high. So first let assume that the clock signal what we have is equal to 0. Clock is equal to 0. Now if the clock is 0, can you tell me like what all the things happens in the circuit if the clock is 0? Can I get a response in the chat? This is the circuit. I hope you understood the circuit now. So initially I am kind of assuming that the clock is 0, and when the clock is 0, what happens in the circuit? Any guesses? Can I get some response in the chat? Yeah, if you look at the transistors, there are three transistors which the clock is controlling. There are three transistors. Mn1 and Mn2 will be equal to 0. Yes, yeah, correct. So when you have when your clock is equal to 0, what I can say is this transistor is based on clock. This is also based on clock. This is also based on clock, right? So when the clock is 0, basically what happens, since you have these two as PMOS and this as NMOS, PMOS transistors will turn on when the clock is low, and NMOS transistor will turn off, right? So let me just write it down there. In the PMOS transistors, PMOS turns on and NMOS turns off, right? So as a result of this, when PMOS turns on, what happens here is this will turn on, and the output node where we marked it as VOM and VOP, both will be pre-charged, or both will be connected to VDD, right? So a PMOS turns on leads to VOM and VOP both equal to VDD. Right, so what happens is whatever is the previous state, when the clock is 0, both output will be pre-charged to VDD, or both output will be reset to VDD. So in that way, we can consider this phase as, when the clock is 0, this phase can be considered as a reset phase. Reset phase or a pre-charge phase, both can be, it can be understood in either way, reset phase or pre-charge phase. And all the previous values, the previous values of VOM, and VOP are erased, and it's VDD now, right? This is with respect to the top transistor PMOS. Now what happens to NMOS transistor? If you look at NMOS, since NMOS turns off, as a result of that, it will actually disable the entire this structure, because if this is off, these two transistors will not draw any current. As a result of that, even all these four transistors also will be off, or will be disabled. So rest of the transistors are disabled. The rest of the circuit is basically disabled, because since it is not drawing any current. You can see that a differential pair is there, where this node is not connected to ground. This is open, or this is off, so this will be disabled. Moreover, the regeneration, the back-to-back inverters also are disabled, because this node is directly connected to VDD. Even though this is VDD, there is no path here for the current to flow, so the transistors are also will be off. So this is one advantage what we mentioned before, that there is no static power dissipation in the case of strong arm latch. When this is off, when the clock is 0, there is no current drawn by the circuit. All right, so I hope this is clear. So this is one important advantage of this. In a strong arm latch, when the circuit is reset, it will not draw any current. Right. So even though we have marked it as like this, no, even though we marked it as like this, and when this becomes short, it is not like you have a inverter enabled as back-to-back inverter enabled with a short. Since it is connected, through this differential pair, and you have a clock, you have a transistor, you have a switch connected over here. This switch shuts off. As a result, no current will be drawn by the circuit. I hope this part is clear. If you are with me, can I get some response in the chat? All right, yeah. So moving on to the second phase, where we'll assume that the clock is 1. Now the clock is 1. Yeah. Now here we'll assume that the clock switches from 0 to 1 and the clock is now 1. So what happens now is, when the moment the clock turns on, what happens in the circuit? Clock turns on means this transistor turns on, right? So this is enabled now. This is enabled now. So whenever this is enabled, so in the previous state, whether VIM is present or not, since the clock is 0 and since the bottom transistor is disabled, that will not draw, or that will not since the differential pair itself is not enabled, there is no sense in having an input signal over there. But now, since the clock is high and the bottom transistor is on, now the differential pair is active, right? So now the differential pair is enabled. This is enabled now. And what happens if the differential pair is enabled, and if a signal is available as VIP and VIM, definitely IP and I, just mark it as IM. So IP and IN starts flowing, right? So as soon as the differential pair is enabled, IP and IM will start flowing. And what happens when the IP and IM starts flowing? What effect you can see in the circuit? The clock is high. This is on. If this is on, based on the input signal available, both transistors MI2 and MI1 will be converting that input differential voltage into a current, right? So can you tell me what will be the condition, in what region the transistor will be, MI1 and MI2 will be when this turns on? What will be the region of operation when at the moment the clock turns high? Any idea? Yeah, it will be in saturation region, because you can see that when the clock in the previous state, when the clock is low, the VOM and VOP, both the nodes, right? These two nodes are connected to a high voltage. So even this VXM and VXP, these two also will be, it is not at a 0 voltage, right? So that is also seems to be at a higher voltage. So when it turns on, so when clock just turns on, the transistors MI1 and MI2 are in saturation, right? So we know that in saturation, yeah, the nodes are pre-charged to be ready, correct? So same MI1 and MI2 are in saturation. So we know that in the transistors in saturation will have maximum GM, and what I'll have as IP and IM is proportional to GM times the difference, right? GM times VIP or GM times VIM. So we'll have a large current depending on the input voltage, or whatever is the difference in the input voltage. The small difference in the input voltage will be translated to a large current because of large or high GM in the saturation. That is what will happen, right? But when the current starts flowing, or when IP and IM starts flowing, what also will happen is, you will see that since the current is flowing, all these nodes are actually getting discharged, right? So we can see that the nodes VOM and VOP, I'll mark here. So as when the current starts flowing, the nodes VOP and VOM, this also starts discharging. or these also, the voltages will lower. It'll reduce, and voltage get reduced, right, at these 2 points. So what is the result of that? So you can think of this way. Initially, right, so initially it is pre-charged, so it is at VDD, right? So both VOP and VOM, so let me mark it as this as VOP. Both are at same level. I'm just using a different color to differentiate it. All right, so this is your VOP and this is VO VOM, right? Both are at VDD initially. Now, when the differential pair turns on, when your IP and IM starts flowing, both these nodes will start discharging. Now, can you tell me, say for example, we'll consider, say your VIP input voltage, VIP is greater than VIM. At this condition, your VIP is greater than VIM. So naturally, what we expect is if your VIP is greater than VIM, your IP will be greater than IN, right? When your the voltage on this side, if it is higher than this side, your IP will be more than IM. If IP is more than IM, what happens here is the current IP is flowing in a large, like IP current will be more than IM current. As a result of that, the nodes on left side will discharge at a faster rate than the nodes at the right side, right? Can I write that here? Are you guys with me? If your input of VIP is more than VIM, the current flowing here will be more than the current flowing here. As a result, the left nodes discharge rapidly. I can say the left nodes discharge rapidly than the right nodes, right? So which are the left nodes? If you look at the circuit, you will see that the left nodes are VXM and VOM. So let me write it as here VXM and VOM will discharge faster than what? Than the other nodes. The other nodes are VOP and VXP. Right. Now, how this affects the operation, or how this helps the comparator to decide or make a suitable decision? What do you think? If your VXM and VOM are discharging at a slower, the VXM and VOM are discharging at a faster rate than the other nodes, what will happen? Ultimately, what will happen? So now we no need to consider the clock, the PMOS clock here, the PMOS switch here. Now we have to only see the regenerative latch, the transistors MP1, MN1, MP2 and MN2, which is connected back to back. Now based on the input signal, this should make a decision. That means it should go to, one side should go to high and the other side should go to low, right? Now what will happen if your VXM and VOM nodes are decreasing at a faster rate, reducing at a faster rate than the other side? What will happen? Let us look at the PMOS transistor condition now. So if you look at the PMOS transistors, we have the PMOS transistors here are, one is MP1 and the other PMOS transistor here is MP2, right? Now what is the voltage here at MP? The gate of MP1 is connected to VOP, so this voltage is VOP, and the gate of MP2 is connected to VOM, right? This is the condition of PMOS transistors. Now what we have seen is the left node your VOM is discharging at a faster rate than VOP, right? So what will happen? Since your VOM is falling more rapidly than this node voltage is falling more rapidly than this one, which transistor will turn on first? Can I get your response? I hope till this point is clear. Based on the input voltage, VIP and VIM, say if your VIP is more than VIM, your current IP, the expected current IP will be more than IM. If that is the case, since your IP current is more than IM current, the nodes on this left side will be discharging at a faster rate than the nodes on the right side. So depending on this node here, say if your VOM is discharging at a faster rate, VOM is connected to the gate of MP2 and VOP is connected to the gate of MP1. Now if this is if the gate of the transistor MP2 is discharging at a faster rate than MP1, which transistor will turn on? Can I get some response? Whether MP1 will turn on, MP2 will turn on. MP2, yes. So as a result of this, since your VOM falls more rapidly, your MP2 turns on first. Right. So what will happen if MP2 turns on first? If MP2 turns on first, this node, the output node will be regenerated, or output node will be connected to VDD, right? So that is on the right side. Now MP2 will turn on first compared to MP1. Now at the same condition, let us look at the transistors MN1 and MN2. What is their condition? Look at this. We have the NMOS transistors in the inverter. These are the NMOS transistors in the inverter. If you look at this node, the voltage what we have is, what is connected to the drain is VOM. So this is VOM. Now the gate is connected to, the gate of this is connected to VOP. This is VOP. Let us, this node is say VXM. Now this is VXP. If this is VOP and this node is actually connected to VOM, this is connected back to this, right? So this is VOM and this is connected to VOP. Sorry, not this. Yeah, correct. Now tell me, out of these two transistors, so this is MN1 and this is MN2. So which will turn on first? Here if you look at this, based on the previous, the same condition, VOM and VXM, right? Because the left hand side's nodes are falling at a faster rate. So since your VOM and VXM falls more rapidly than the VOP, which is on the right side, since these two falls first, what happens? VOP is still high, but these two transistors are lowering. So the transistor MN1 turns on first before the transistor MN2. Right. So if you look at the latch circuit, the clock is high, so this is on. Based on that, the differential input pair, the initial condition is established depending on VIP and VIM. Since the transistors are in saturation, it will convert the small difference in input voltage to a large current. Based on that large current, the current IP and IM starts flowing. And since your IP and IM starts flowing, and since your IP is more than IM, the nodes VXM and VOM will discharge at a faster rate. So since your VOM and VXM is discharging at a faster rate, on this side, on left hand side, your on left hand side this turns off. So, or you can say that MP2 turns on first and MN1 turns on first from the back to back latch. So as a result of this, what happens? Since your MP2 turns on first, this node will be charged to VDD, and since your MN1 turns on first, this node will be pulled down to 0. Alright, so it will pull the right side node will be pulled to VDD or regenerated to VDD, and the left side node will be regenerated to ground. So this is how this latch circuit works based on an input signal available at the gate VIP and VIM. Alright, so if I look at the waveform here, say your VOP and VOM both are at this point. So let me now we know that your VOM is discharging, falls more rapidly. So if your VOM falls like this, it will fall. then your VOP also falls, right? VOP falls at a slower rate than VOM, so let the VOP also fall here. But when it starts lowering, what happens? The transistors MP2 and MN1 will turn on accordingly and will pull the nodes VOP and VOM to, or it will help VOP and VOM to make a decision, right? In this case, what happens? Your VOP goes back or regenerates and go back to VDD, where your VOM will discharge and finally come down to 0, right? So you can see that here, somewhere here, somewhere at this point, that regeneration starts, right? So when your VOP and VOM start discharging at some point, when the transistors MP1 and MP2 and MN1 turns on, that makes this can be understood as the onset of regeneration phase. The regeneration starts somewhere here. Now, can you tell me where is the in the previous latch? Now, if you remember, in the previous latch, we specifically mentioned about the sampling instant. Sampling instant is the specific voltage which is taken and which is regenerated, right? Can you tell me what is the sampling instant in this case? What is the sampling instant in this case? All right, one more thing I forgot to mention. So what happens when the node VXM, right, these two nodes starts falling, will keep on start falling at some specific point. The transistors Mi1 and Mi2, initially it was in saturation, but what happens, Mi1 and Mi2 will, as these voltages are start reducing, these two transistors will move from saturation to linear, right? When the transistors move from saturation to linear, even this relation also will not be that strong, right? Because when the transistors move from saturation to linear, the GM also will be accordingly small, because the GM then becomes proportional to the VDS voltage, which is turning low in this case. So the influence of the transistors Mi1 and Mi2, or I can say that the input will not have any influence on the circuit when VXM and VXP starts reducing. As a result, the latch or the back-to-back inverters can actually make a decision here, right? So can you tell me what is a sampling instant here? Are you guys with me? So as we have seen in the previous circuit, a previous circuit, sampling instant is actually the falling, like as soon as the clock falls, like clock goes from high to low, that is a sampling instant what we are considering. But in this case, the sampling instant is not that specific or abrupt. The sampling instant is somewhere here, because we do not know when the watt voltage actually it is taking up. Now we know only when the transistors VOP and VOM, the voltages VOP and VOM, when it starts reducing at some point of time, when these two transistors turns on, it will start regenerating. So your sampling instant is somewhere there in this range, right? The sampling instant is somewhere there in this range. We will not be able to say exactly this is a sampling instant, but sampling instant is there, and regeneration, when the regeneration starts, depending on that voltage, it will be regenerated to either high or low. All right. So is this clear? Any questions on this?